Give me 30 minutes, and I will make RoPE click forever. You've probably heard of models like Llama 3, Palm, and GPT Neo X. But here's the thing, they have all abandoned the old way of embedding texts. So what do they use instead? They use rotary positional encoding, or RoPE for short. And what's the big secret behind this incredibly powerful technique? What if I told you it was this? As you see on the screen, this is the entire secret. We have a 2x2 matrix with cosine m theta, negative sine m theta, sine m theta, and cosine m theta, multiplied by a simple two-dimensional vector. That's it. It's just a simple 2D rotation. I'm not kidding. High school trigonometry is powering the world's most advanced AI. And what's so special about it? It unlocks relative positional information. That is the key. Now, here is my promise to you. This is our destination. On the screen, you can see a Python function, def apply rotary pos ember. It probably looks pretty intimidating right now, but we will explain every single line. So stick with me. We're going to do this step by step, from first principles. So to really understand RoPE and why it's such a breakthrough, we first have to understand the old way of text embedding, the method it replaced. We have to talk about absolute positional embeddings. Think of it like this. It's a street address for every single word. So how did the early transformers, models like BERT and GPT-2, actually know where a word was in a sentence? Well, the formula was actually surprisingly simple. You take the token vector, which represents the word's meaning, and you just add the position vector, which represents its location. That's it. The meaning vector and the location vector get summed up to create the final input. Let's look at a concrete example. Say we have the phrase, the red car. As you can see in this table, for the word the at position 0, the math is just the vector for the plus the vector for position 0. Easy. For the word red at position 1, it's the vector for red plus the vector for position 1. And for car at position 2, I think you see the pattern. It's the vector for car plus the vector for position 2. Simple, right? Yeah, and this is where the entire system starts to break down. Here's the fundamental problem. Language is relative. But these addresses we're giving each word, they're absolute. And that is a huge mismatch. Let me show you just how big this flaw is. Let's look at shifting positions. On the screen, you see two sentences. The first is, the red car is fast. In this sentence, the word red is at position 1. The second sentence is, I saw the red car. Now the word red is at position 3. Now let's look at the actual input vector the model gets for the word red in both cases. In sentence 1, the input is the vector for red plus the vector for position 1. Okay, but in sentence 2, the input is the vector for red plus the vector for position 3. These are completely different vectors for the exact same word. The model sees two totally unrelated inputs, even though the core meaning of red hasn't changed at all. So what does this mean in practice? It means the model has to relearn the meaning of a word and its relationship to other words at every single position. It's massively inefficient. Clearly, this is not the way. We need a system that's built from the ground up on relative distance. So what's the goal? What's the dream system we're trying to build? The attention score between two words should depend only on two things: their content, represented by the query and key vectors q and k, and their relative distance, which we can write as m minus n. The final score should not depend on the absolute positions m and n separately. That's the key. So where does RoPE fit into all this? Before we dive into the solution, let's get a few key questions out of the way. First question, which vectors get RoPE applied to them? The answer is only the query, or q, and key, or k, vectors. We do not apply it to the value vector. Second question, is RoPE learned? No. This is a big one. The rotations are fixed deterministic math. It's not something the model has to figure out through training. And finally, where is it applied? It's applied in every single attention block, independently, at every layer of the model. So here's the billion-dollar question. How do we add positional information without completely destroying the original semantic meaning of the token? How do we get the best of both worlds? And the answer is so elegant. We don't add. We rotate. This simple idea is what I call the geometric split, and it is the entire foundation of RoPE. Here's how it works. We take a vector and we split its properties into two distinct jobs. First, the length of the vector, its norm, continues to represent the semantic meaning of the word, the what. And second, the direction of the vector, its angle, now represents the token position, the where.
Do you see how brilliant this is? We can now change the position just by changing the direction without touching the length, and therefore without corrupting the original meaning. It's a perfect separation of concerns.
Okay, so how do we actually do this rotation? Let's forget about giant language models for a second and go all the way back to high school math. You might remember the standard 2D rotation matrix. You can see it on the slide here, the famous R of theta formula. To rotate any vector v, you just multiply it by this matrix. That's it. The new vector, v prime, is just R of theta times v. All right, let's make this super concrete. Let's take a simple vector, v equals 1, 2, and we're going to rotate it by a nice clean 90 degrees, which is pi over 2 radians. Let's do this manually right here. First things first, we know the values for a 90-degree rotation. The cosine of 90 degrees is 0, and the sine of 90 degrees is 1. So when we plug that into our rotation matrix, it becomes incredibly simple. As you can see, R of 90 degrees is just the matrix with 0 and minus 1 in the first row and 1 and 0 in the second. Now we just multiply. V prime is that matrix times our vector 1, 2. Let's do the math. 0 times 1 plus minus 1 times 2, that gives us minus 2 for the top value. And then 1 times 1 plus 0 times 2 gives us 1 for the bottom value. And there it is. Our new vector is minus 2, 1. And you can see this perfectly on the graph. The original vector points to 1, 2, and the rotated vector points to minus 2, 1. A perfect 90-degree counterclockwise spin. But here's the most important question. The whole reason we're doing this. Did we change the length? Let's check. The original length using Pythagoras is the square root of 1 squared plus 2 squared, which is the square root of 5. Okay, now for the rotated vector. Its length is the square root of minus 2 squared plus 1 squared, which is the square root of 4 plus 1, which is again the square root of 5. Yes, the length is perfectly preserved. Our semantic meaning is completely intact. We've only changed where it's pointing. Okay, so we've established our tool, rotation, but now we have to connect it back to our original problem. How do we turn a simple integer position, like position 0, position 1, position 2, into a rotation angle? The rule is beautifully simple. As you see on the slide, the angle of rotation is just the token's position, which we'll call m, multiplied by some constant base angle, which we'll call theta. That's the entire rule. Let's look at this table on the screen to see how this rotation schedule plays out. For a token at position 0, the rotation angle is 0 times theta, which is 0. No rotation. It's our baseline. For a token at position 1, we rotate it by 1 times theta, just a small spin. For a token at position 2, we rotate it by 2 times theta, a double spin. And for position 3, you guessed it, 3 times theta, a triple spin. It's a simple, predictable, linear progression. The further the token, the more we spin it. And when you visualize this, what do you get? You get this beautiful geometric shape, a helix. As you can see in this animation, As the position, which is the z-axis, increases, the vector rotates cleanly through the xy plane. Each step up in position corresponds to a predictable twist in the spiral. It's an incredibly elegant way to map a discrete sequence of positions onto a smooth, continuous geometric path. So, we've cracked the code. We've figured out how to encode position without destroying meaning in 2 dimensions. But here is the challenge. Llama 3 and models like it don't use 2D vectors. They use vectors with 4,096 dimensions. How do you rotate a 4,096 dimensional vector? I mean, seriously think about that. A direct approach would be a 4096 by 4096 matrix. That's over 16 million numbers just to rotate one vector. It would be a computational nightmare. But of course, that's not what we do. The solution is far more elegant. We don't do one big rotation. We do 2,048 small ones. Here's the core strategy. It's called the pairwise split. Imagine our input vector, x0, x1, x2, all the way down to the end. Instead of treating it as one giant block, we chop it up. As you can see in this diagram, we group them into pairs. x0 and x1 become pair 0, x2 and x3 become pair 1, and we just keep doing this all the way down the vector. Simple, right? We've turned one massive problem into thousands of tiny 2D problems we already know how to solve. But here's the catch. If they all rotate at the same speed, it's completely ambiguous. It doesn't tell us anything useful. We need a way to make each pair's rotation unique. And the inspiration for this is a simple analog clock. A clock has a fast second hand, a medium minute hand, and a slow hour hand. They all rotate, but at different speeds. Why is this important? Because it's the combination of those different speeds that gives every single moment a unique signature. You need all 3 to know the precise time. RoPE uses this exact same idea. Each pair of dimensions is a clock hand that rotates at a different speed. The first pairs spin fast, like the second hand. The last pairs spin very, very slowly, like the hour hand. And how do we control that speed? With this beautiful little formula you see right here. This is the frequency formula. The speed for the ith pair, theta I, is 10,000 to the power of negative 2i over d. Let's break that down. When I is 0 for the very first pair, the exponent is 0, so theta is 1. That's fast. But when I is large for the last pairs, the exponent becomes a bigger negative number, so theta gets tiny, close to 0. That's slow. So putting it all together, here is the full algorithm. For any vector x at position m, and for each pair I, first we calculate that frequency, theta I, using the formula we just saw. Second, we calculate the final angle by simply multiplying the position m by that frequency. And third, we use that angle to rotate the pair of values x2i and x2i plus 1. That's it. Repeat for every pair, and you're done. Let's make this crystal clear with an example. Imagine a simple 4-dimensional vector with the values 1.0, 0.5, 0.8, and 0.3. And let's say it's at position m equals 2. The dimension d is 4. Okay, let's calculate the rotation for pair 0. That's the first 2 numbers, 1.0 and 0.5. The index here is I equals 0. So the frequency, theta 0, is 10,000 to the power of 0, which is just 1. This is our fast rotator. The final angle is the position, 2, times our frequency, 1, which is 2 radians. When we apply that rotation, look at the result on the slide. The vector changes from 1, 0.5 to negative 0.875, 0.7. That is a significant change. Now let's do pair 1. The values are 0.8 and 0.3. The index is I equals 1. The frequency, theta 1, is 10,000 to the power of negative 0.5. which comes out to a tiny 0.01. This is our slow rotator. The angle is position 2 times 0.01, which is just 0.02 radians, a very small angle. And the resulting vector? It barely moved, from 0.8, 0.3 to 0.794, 0.316. So let's look at the final result. Our vector started as 1.0, 0.5, 0.8, 0.3, and after the RoPE transformation for position 2, it became negative 0.875, 0.7, and 0.794, 0.316. The first pair rotated a lot. The second pair rotated just a little. This whole system is deterministic. There's no randomness. It's parameter-free. We don't need to train millions of weights for it. It requires zero learning. It's just pure, elegant math. We have built the machine. We have the full algorithm. But the final, most important question remains. Why does this work?
We have the intuition. We understand the what and the how. Now, we need the proof. So let's zoom out for just a second. How does a transformer decide what matters? It all comes down to the attention formula you see on the screen. Attention equals softmax of Q K transpose times V. But the real magic, the core of the whole thing, happens right there in that Q dot K transpose term. It's all about the dot product. So here's our mission. We must prove that the dot product depends only on two things. First, the original content, the Q and the K vectors. And second, their relative distance, m minus n. As you can see in the formula, we need to show the score is some function g of q, k, and m minus n. The absolute positions, m and n, must vanish completely. They have to disappear. All right, let's set up the proof. The beauty here is that we only need to prove this for a single two-dimensional pair of values. We have a query vector, q, at position m, and a key vector, k, at position n, and they share a rotation frequency, theta. So, step 1, we apply RoPE. First, we rotate the query, q. The new query, q prime, is the rotation matrix for m, theta, times q. Second, we do the same for the key. The new key, k prime, is the rotation matrix for n, theta, times k. Simple enough. Okay, on to step 3, the dot product. The final score is the transpose of q prime times k prime. So let's substitute the definitions we just made. You can see it on the slide. The score is r m theta q, all transposed, times r n theta k. Now, we use a standard rule from linear algebra, that A B transpose equals B transpose A transpose. Applying that rule gives us the next line. Score equals Q transpose times R M theta transpose times R n theta times K. Look at that. Everything comes down to simplifying that middle term. That is where the magic happens. And to solve it, we have two secret weapons. Two beautiful properties of rotation matrices. First, the transpose is the inverse. Rotating backwards is just using a negative angle. So the transpose of r of alpha is just r of negative alpha. Second, multiplication adds the angles. Two rotations, r alpha and r beta, combine into a single rotation, r of alpha plus beta. These two rules are everything we need. Okay, let's solve that middle term. We start with r of m theta transpose times r of n theta. Step 1, apply the transpose rule. That first term becomes r
of negative m theta. Step 2, apply the addition rule. We combine the two rotations by adding their angles. So we get r of n theta minus m theta. And for the final beautiful step, we just factor out theta. We are left with r of n minus m times theta. And there it is. The absolute positions, m and n, have completely canceled out. The only thing left is their relative distance. Incredible. Mission accomplished. Let's look at the final score. It's Q transpose times that single rotation matrix we just found times K. And what does it depend on? The original content, Q and K, and the relative position, n minus m. That's it. The math is just beautiful. It's so elegant. But here's the billion-dollar question. Can we actually code it? The answer is yes. And our goal is to create a simple drop-in function that you can use for any transformer. Here's the blueprint. It's a really clean two-part strategy. First, pre-compute. We're going to calculate all the rotation angles we'll ever need just once and store them in a lookup table. Think of it as a cache. Then, step 2, apply. We'll take those cached angles and use them to rotate our vectors on the fly during the forward pass. Okay, let's dive into part 1, pre-compute. The whole idea here is to do the heavy lifting early, so our model doesn't have to think about it later. Now, you'll recall our formula for the ith pair of dimensions. Theta I equals 1 divided by the base raised to the power of 2i over d. It looks a little intimidating, but it's not. The base is usually just a big number, like 10,000. That 2i over d part just creates evenly spaced steps across our head dimension d. That's all it's doing. So let's see how this translates to code. We're defining a function, pre-compute RoPE hobby. The very first step is to calculate those frequencies. Look at this line for inv_freq. 1.0 over base to the power of torch.arrange. This is a direct translation of that formula. This single line creates all the different speeds for our spinning clocks. So, for a head dimension of 128, this gives us 64 unique frequencies. Next up, the angles. For this, we need the positions. We create a tensor T that just holds our position indices, 0, 1, 2, 3, and so on, up to the maximum sequence length. And now for the core operation. We calculate the final angles using an outer product. This line, torch.einsum ij temperature ij, is a super efficient way to multiply every position by every frequency. The result is a big table that contains every single angle for every position for every dimension pair. It's all pre-calculated. But we have one final step. We need to format this for our vector pairs. Remember, x0 and x1 both need the same rotation angle. So we use repeat interleave to duplicate the values. An angle list that looks like theta 0, theta 1 becomes theta 0, theta 0, theta 1, theta 1. And now our lookup table is complete. All right, part 2, the application. This is where we implement the famous rotation trick. Here's the thing you need to know about deep learning. Loops are slow, terribly slow. We can't be iterating through dimensions. We need to do everything at once. We need vectorization. So how do we do that? Let's look at the standard rotation formula again. X prime equals x cos theta minus y sine theta, and so on. We can actually rewrite this with vectors. As you can see in this formula, it becomes the original vector xy multiplied by cosine theta plus a special partner vector, negative yx, multiplied by sine theta. The whole key to vectorizing this rotation is creating that partner vector. And creating the partner is incredibly simple. If your original pair is x0, x1, you just swap them and negate the new first element. The partner becomes negative x1, x0. That's the whole trick. Let's see it in the final function. Apply rotary pause mem. Step 1 is preparation. We slice our big embedding table to match the sequence length of our input. Then we do some squarely operations. This is just reshaping the tensor. It's a bit of PyTorch plumbing to make sure the shapes will align perfectly for broadcasting. Then we calculate the cosine and the sine of all our angles. Okay, now for step 2, the swap. This is the magic line right here. We reshape x to view it in pairs, and then torch.stack with negative x reshaped 1 and x reshaped 0. This is it. This one elegant line creates that special partner vector, that negative x1, x0 for every single pair, across every head, across the entire batch, all in one go. Which brings us to the final step, the rotation. It's one line. X times cosine plus x partner times sine. That's our vectorized formula. In this single line of code, we are performing potentially millions of 2D rotations, all in parallel. And I want to be clear, this is not a toy example. This is reality. Let's look at Llama 3 8b. Its embedding dimension is 4096. It has 32 attention heads. Its context window is 8192 tokens. When Llama 3 processes your prompt, it calls this exact apply rotary pause m function 32 times. Once for the queries and once for the keys in every single attention head. It's simple code, but it has a massive impact. We started with a matrix. We ended with a standard. So let's recap exactly how we got here. First, we identified the core problem. Absolute positional embeddings were rigid. They forced models to constantly relearn the simple idea of one step away in every single new context. Then came the intuition, the core insight. Position is rotation. This brilliant idea lets us inject positional information without corrupting a token's original meaning, because remember, rotation keeps the vector's length constant. From there, we figured out how to scale. We created a symphony of clocks. We rotated pairs of dimensions at different speeds, creating these unique, high-fidelity signatures for every single position in a sequence. And the payoff? The mathematical guarantee. We walked through the proof, and as you can see in this final formula, the attention score is only a function of the relative distance, m minus n. The absolute positions just vanished. This entire journey from a simple idea to a full PyTorch implementation reveals a deep principle in machine learning. It's the power of inductive bias. Think about it. There are two ways you can teach a model about the world. There's the hard way, the blank slate approach. You force the model to learn the fundamental concept of distance from trillions of examples. What's the result? It's brute force. It's wildly inefficient. And then there's the RoPE way, the inductive bias approach. We don't make the model learn about relative distance, we build it in. We build that idea directly into the geometry of the space itself. The result? It is correct from day one. Instead of starting from 0, we gave the model a head start. That's why RoPE isn't just some clever hack. It is a masterclass in model design. The magic, the thing that felt so complex and mysterious at the beginning, it hasn't disappeared. It has simply dissolved into elegant, understandable mathematics.